Right now, wherever you are, lying there in the dark with the covers pulled up, something is happening inside you that you will never feel. Not once, not for a single second of your entire life. Every hydrogen atom in your body, and there are an almost unthinkable number of them, mostly living inside the water that makes up most of your mass, is spinning. Has been spinning since before you were born. Will keep spinning tonight, through every stage of sleep you pass through, and tomorrow, and for as long as you're alive. You've never noticed it. Nobody has. There's no sensation attached to it at all. It's just there, quietly happening, the way your heartbeat is there. Except you can at least feel your heartbeat if you press 2 fingers to your wrist. This you can't feel no matter what you do. And here's the strange part. That invisible spinning can be made to answer. If you put a person inside a strong enough magnet, and then send in a very precisely tuned pulse of radio energy, the same broad category of energy your car radio quietly pulls out of the air, those spinning atoms respond. They answer back. And it turns out that if you listen closely enough to that answer, carefully enough, patiently enough, you can reconstruct a detailed picture of the inside of a living human body. Slice by slice. No incision, no radiation, nothing cut open, nothing burned, nothing broken. You've probably been inside one of these machines yourself, or you know someone who has. A loud tube, a tight tunnel, that strange thumping, banging sound that seems completely at odds with a hospital procedure. And almost nobody who has ever been inside one has any real idea what is actually happening in there while it runs. What that noise means. What that magnet is doing to the atoms in their own hydrogen-rich body while they lie still and try not to think about the walls being close. Tonight, we're going to slowly work through all of it. Where the idea came from, who fought for it, who got left out of the credit they probably deserved, how the machine is actually built, and why it makes that unbelievable racket. There's no rush at all. This is one of those long, winding stories, and if you drift off somewhere in the middle, that's completely fine. The ideas will still be here waiting whenever you want to pick them back up. Let's start at the very beginning, with a question that sounds almost too simple to be important. What is spin, actually? Here's the thing about the word spin. The moment you hear it, you probably picture something like a top, or a coin wobbling on a table before it settles, or maybe a planet turning on its axis. And that picture isn't wrong, exactly, but it's also not quite right. And the gap between the picture and the reality is where a lot of the strangeness in this story lives. Let's build it slowly, the way you'd build anything you actually wanted to understand rather than just memorize. Start with something ordinary. A spinning top on a table. It has mass, it's rotating, and because it's rotating, it has what physicists call angular momentum, which is really just a fancy way of describing how much rotational motion something has and in what direction. Nothing mysterious yet. Now imagine the top is also electrically charged, somehow, magically, charged all over its surface. A rotating electric charge does something extra. It creates a tiny magnetic field, the same basic kind of field a bar magnet makes, with a north end and a south end. Moving charge makes magnetism. That's just electromagnetism, plain and ordinary. The same stuff that makes your refrigerator magnets stick and your car's alternator generate electricity. So now you have a spinning, charged top that behaves, from the outside, sort of like a tiny compass needle. It has a preferred direction it likes to point. That combination, the spin and the tiny magnetic personality that comes along with it, is called a magnetic moment. And this is where things get interesting, because it turns out that protons, the positively charged particles sitting at the heart of atoms, behave almost exactly like this. Not literally spinning balls of charge. That picture breaks down if you push on it too hard. Quantum objects are stranger than that. But for our purposes tonight, the analogy holds up beautifully. A proton has an intrinsic property called spin. It carries electric charge, and the combination gives it a tiny magnetic personality. Every single proton in your body, in the water in your cells, in the calcium in your bones, is a microscopic bar magnet. Always has been, always will be. Now here's where it becomes something you can actually work with. Take a person, take you, lying there right now, and put your entire body inside an enormously strong magnetic field, thousands of times stronger than the Earth's own magnetic field. What happens to all those trillions and trillions of tiny proton bar magnets scattered through your tissue? You might expect they'd all snap into perfect alignment, like a room full of compass needles suddenly all pointing north. But that's not what happens. And the reason it doesn't happen is actually the whole secret at the heart of this entire technology, so it's worth sitting with for a moment. At body temperature, thermal energy is constantly jostling everything around, knocking those tiny magnetic protons this way and that, fighting against the external field's attempt to line them all up. The external magnet wins, but only barely. Only just barely. For every million protons in that magnetic field, roughly, only a handful more will end up aligned with the field than against it. A tiny, tiny statistical excess. Most of them cancel each other out completely, one pointing with the field, one pointing against it, canceling, 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 all the way down, until you're left with this whisper-thin surplus. And that whisper-thin surplus, that small asymmetry among trillions upon trillions of atoms, is the entire game. It's worth lingering on that, because it seems almost absurd that something so faint could be the foundation for an entire medical imaging technology. But it is. It's all we have to work with. Everything that follows, everything about building this machine, all of its engineering brutality, comes down to trying to detect and manipulate a signal that starts out being generated by a tiny fraction of the atoms in your body. But that surplus isn't just sitting there passively, either. Here's the next layer, and it's the one that actually makes everything work. Those aligned protons don't sit perfectly still, lined up like soldiers at attention. They wobble. Think about a spinning top again, but this time, imagine you've nudged it slightly off its vertical axis while it's still spinning fast. It doesn't just fall over. It traces out a cone shape as it spins, its axis slowly sweeping around in a circle even while the top itself keeps spinning rapidly. That slow, circling wobble has a name. It's called precession. You've probably seen it without knowing the word for it. Watched a top or a gyroscope trace that lazy circling motion right before it finally loses momentum and falls. Protons in a strong magnetic field do the same thing. They don't just align with the field like a compass needle settling flat. They precess around it, tracing out that same cone-shaped wobble, spinning on their own axis while that axis itself slowly sweeps around the direction of the external magnetic field. And here's the detail that changes everything. The rate of that wobble, how fast the precession happens, isn't random. It's determined precisely by the strength of the magnetic field the proton is sitting in. Stronger field, faster wobble. Weaker field, slower wobble. There's an exact, fixed, dependable relationship between the two, and that relationship is going to turn out to be the master key that unlocks the entire imaging process, though we're getting ahead of ourselves. For now, just hold on to the image. Trillions of tiny magnetic protons, a small statistical majority tipped into alignment by an enormous external magnet, and every single one of them precessing, wobbling, at a rate set exactly by the strength of the field around it. It helps to sit with the scale of that surplus for a moment longer, because numbers like this are easy to say and hard to actually feel. Picture 2 million protons, lined up in your imagination like an audience filling a stadium, half of them pointing one direction, half pointing the other, canceling out pair by pair the way opposing forces always do. Now imagine that instead of an exact even split, the count comes out just slightly lopsided. Not by much. Somewhere in the range of a handful extra, out of that entire stadium of 2 million, tipped toward alignment with the external field rather than against it. That handful, that almost embarrassingly small imbalance, is the entire source of every signal an imaging machine will ever pick up from a living human body. Every image ever produced by this technology, every tumor ever detected, every torn ligament ever confirmed, traces back to a surplus that's small, multiplied across the almost incomprehensible number of hydrogen atoms packed in a human tissue, which is itself so large that even a whisper-thin fractional imbalance adds up to something detectable, if you know precisely how to listen for it. And that's really the quiet, elegant secret sitting underneath this entire field. You don't need every proton to cooperate. You don't need a booming, obvious signal. You need a magnet strong enough and instruments sensitive enough to catch the faint, collective murmur of just the tiny fraction that happened to be facing the right way. And then you need a way to make that murmur answer back clearly enough to be worth listening to. There's another layer worth adding to the precession picture before we move forward, because it explains why the wobble itself is so useful rather than just being a strange side detail. A proton precessing around the external magnetic field is, in effect, a tiny rotating magnet, and a rotating magnet generates a small, oscillating electrical signal in anything positioned nearby that's built to detect it. The same basic principle behind how a bicycle dynamo generates electricity from a spinning wheel, or how a generator at a power plant converts mechanical rotation into usable current. A precessing proton, then, isn't just a passive, static compass needle sitting there uselessly. It's an active, tiny, rhythmically oscillating source of radio frequency energy, faint almost beyond imagining for any single proton, but summed across that statistical surplus spread through billions of cells, potentially detectable, if you can build a receiver quiet enough and precise enough to hear it. So here's where Act 1 leaves us. And it's worth ending on this question because it's the same question that would occupy the smartest physicists in the world for the better part of 2 decades. If these tiny protons are wobbling in a way that produces no visible effect whatsoever, nothing you could see, nothing you could feel, nothing that shows up if you just look at a glass of water or a block of paraffin sitting on a table, how could anyone possibly have discovered that this wobble was even happening in the first place? How do you detect something that leaves no trace at all to the naked eye? That question sat unanswered until the 1930s, and it was answered, first, by an unglamorous, unassuming, deeply careful physicist working in a basement laboratory at Columbia University in New York. His name was Isidore Rabi, and his part of this story deserves some real time, because most of what gets told about Rabi centers on his much more famous, more dramatic later work. You may have heard his name before in connection with the Manhattan Project, where he served as a senior advisor, walking that tightrope between deep involvement in the science and a lingering personal discomfort with the whole enterprise, close enough to everything that happened at Los Alamos to have real influence, but never willing to fully join the project himself. That's the version of Rabi most stories tell. But the story we want tonight happened years earlier, when Rabi was younger, quieter, and working through a problem that had nothing to do with weapons and everything to do with a stubborn, patient curiosity about how atoms actually behave. Rabi was born in 1898 in a small town in what is now Poland, and his family emigrated to New York when he was an infant. He grew up in a Yiddish-speaking household on the Lower East Side, and by his own account, he found his way to physics almost accidentally, drawn less by any grand ambition and more by a simple, persistent need to understand how things actually worked underneath their surface. He earned his doctorate at Columbia in 1927, and then spent a couple of years touring the great European physics laboratories, absorbing the ideas that were reshaping physics at exactly that moment, quantum mechanics still fresh, still being argued over, still being worked out by people barely older than he was. Those European years mattered enormously, and it's worth lingering on them a little, because they shaped the particular, methodical style Rabi would carry back with him to New York. He spent time in Zurich, in Hamburg, in Leipzig, in Copenhagen, moving through laboratories where quantum mechanics was still being argued over in real time, sitting in on discussions with some of the very people who had built the theory in the first place. He wasn't a headline name yet during this period. He was closer to a quiet, careful student of the field, absorbing technique, absorbing habits of mind, learning how the best experimentalists of the era actually approached a problem, patiently, skeptically, never satisfied with a result until it had been checked and rechecked. Colleagues from this period would later describe him as unusually direct, unwilling to accept a fashionable idea just because respected people believed it, the kind of scientist who wanted to see the data himself before he'd commit to a conclusion. That habit of mind would serve him extraordinarily well once he returned home and started building his own laboratory from scratch. When Rabi returned to Columbia, he set up what became known as his molecular beam laboratory, and the technique he refined there is worth walking through slowly, because it's genuinely elegant, in the same unhurried, mechanical way that some of the classic physics experiments from this era tend to be. You take a small oven, heat up a sample until molecules boil off it as a thin stream, a beam, of individual molecules traveling in roughly the same direction through a vacuum chamber. This beam then passes through a sequence of carefully shaped magnetic fields. The first field is inhomogeneous, meaning it's stronger on one side than the other, and it has the effect of sorting the beam by the magnetic properties of the individual molecules passing through it, nudging some one way, some another way, depending on how their internal magnetism is oriented. A second magnetic field, further down the apparatus, undoes that sorting if nothing has disturbed the molecules in between. And in between those two fields, Robbie placed a third region, a region of uniform magnetic field, and crucially, an oscillating radio frequency field superimposed right on top of it. Here is the beautiful part. If you tune that radio frequency field to exactly the right frequency, the frequency that matches the natural wobble, the precession of the molecules passing through, something happens. The radio energy gets absorbed. It flips the orientation of the molecule's tiny internal magnet. And once that flip happens, the second sorting magnet, the one meant to undo the first, no longer sorts the molecule back the way it came. It gets deflected differently. Fewer molecules make it all the way to the detector at the far end of the apparatus. So if you slowly sweep the frequency of that radio field up and down and watch the number of molecules arriving at your detector, you see a sudden, sharp dip right at the exact frequency that matches the resonance. Everywhere else, nothing. Right at that one frequency, a dip, a resonance. That's the whole trick. Resonance. The same basic idea as a wine glass that only shatters at one particular pitch, or a swing that only builds up real height if you push it at exactly the right rhythm. Robbie's molecules were absorbing energy only at the one frequency that matched their own internal wobble, and by finding that frequency precisely, he could work out, with extraordinary accuracy, the exact magnetic properties of the nucleus at the center of each molecule. This was the technique Robbie and his colleagues perfected through the mid to late 1930s, published carefully, methodically, in a series of papers that read, even now, like a masterclass in patient experimental physics. It won him the Nobel Prize in Physics in 1944, awarded for what the committee called his resonance method for recording the magnetic properties of atomic nuclei. But notice something important about what Robbie had actually built. His technique worked on a beam, a thin stream of individual, isolated molecules traveling through a vacuum, one at a time, essentially, each molecule interacting with the apparatus more or less on its own. That's a world away from a block of paraffin sitting on a lab bench. It's an even further world away from a human body lying on a table. Detecting resonance in an isolated beam of molecules in a vacuum chamber is one kind of problem. Detecting that same resonance happening inside an ordinary chunk of solid or liquid matter, where trillions upon trillions of nuclei are packed together, jostling against each other, embedded in all the complicated chemistry of real material. That's an entirely different, much harder problem. And for almost a decade after Robbie's breakthrough, that gap between beam and bulk matter simply sat there, unsolved, while the world went to war and physics itself got redirected toward far more urgent, far more devastating priorities. It wasn't until just after the war ended that two separate groups of researchers, working independently of each other on opposite coasts of the United States, without knowing what the other was doing, finally closed that gap. And the way it happened has become one of those recurring patterns you find again and again in the history of physics, the pattern of simultaneous discovery, where an idea seems to be sitting there in the air, almost ready, waiting for whoever gets to it first. On one coast, at Stanford, there was Felix Bloch, a Swiss-born physicist who had already made his name in quantum theory before turning his considerable talents toward this particular problem. Bloch had studied under some of the great names of European physics in the 1920s, had worked through the theoretical foundations of how electrons behave in crystalline solids, and had, along the way, already developed a deep theoretical fluency with exactly the kind of quantum mechanical spin behavior that nuclear magnetic resonance depends on. He'd emigrated to the United States in the 1930s as the political situation in Europe grew steadily more dangerous, eventually settling at Stanford, where his theoretical background in spin physics positioned him almost perfectly to recognize, once the post-war period opened new experimental possibilities, that bulk matter detection might finally be within reach. On the other coast, at Harvard, there was Edward Purcell, an American physicist who had spent the war years doing radar research at the Massachusetts Institute of Technology's Radiation Laboratory, one of the most intensely productive wartime research efforts in American history, developing microwave technology that would go on to shape decades of post-war physics far beyond its original military purpose. That wartime radar work left Purcell with a deep, practical fluency in exactly the kind of radio frequency electronics, generating precise pulses, detecting extremely faint returning signals, filtering out noise, that this new problem demanded. It's a pattern worth noticing, because it shows up again and again throughout the history of technology, the way wartime research, driven by entirely different, often grim motivations, so often leaves behind a residue of technical skill and equipment that later gets redirected towards something as quietly beneficial as looking gently inside a living human body. Neither man was in contact with the other, at least not about this specific line of research. Both were chasing the same fundamental goal, to detect nuclear magnetic resonance not in an isolated beam of molecules, but in an ordinary sample of bulk matter. A block of paraffin, a jar of water. Purcell's team at Harvard got there first, by a matter of weeks, in December of 1945, detecting a faint resonance signal in a block of paraffin wax. Bloch's team at Stanford, working with water, confirmed their own detection just a short time later, in early 1946. Both approaches worked, and remarkably, both groups had arrived at essentially the same physical phenomenon through somewhat different theoretical framings, different enough that for a while the field genuinely used two separate names, Bloch calling it nuclear induction, Purcell calling it nuclear magnetic resonance, before the field eventually settled, mostly, on Purcell's terminology. There was no bitter rivalry here, no wounded egos, no decades-long feud over who deserved more credit. That kind of story exists elsewhere in the history of science, and we'll leave it for other nights. This one resolved cleanly and warmly. In 1952, Bloch and Purcell shared the Nobel Prize in Physics, the committee recognizing that both men had, independently and almost simultaneously, cracked open the same door. Two physicists, from two rival universities, each racing toward the same finish line without knowing the other was even in the race, arriving close enough together that history simply decided to credit them both. And for the next 2 decades or so, that's where nuclear magnetic resonance stayed. A laboratory tool, an instrument for chemists and physicists studying molecular structure, probing the environment around individual atoms within a molecule by looking at subtle shifts in their resonance frequencies, a technique that would eventually become absolutely central to organic chemistry, letting scientists work out the detailed architecture of complex molecules without ever having to see them directly. It was powerful. It was respected. Chemistry departments around the world built their research programs around it. But it stayed exactly where it had been born, in the world of small samples, tubes of purified liquid, careful laboratory conditions. Nobody, not Robbie, not Bloch, not Purcell, imagined that a human body might one day be slid into a machine built on this same underlying physics. Nobody imagined a hospital. Nobody imagined a patient. That leap, from chemistry bench to hospital hallway, needed a different kind of person entirely, someone stubborn enough and strange enough to ask a question nobody else in the field was asking. Let's reset the stakes for a moment, because it's worth appreciating just how far apart these two worlds actually were. Chemists using nuclear magnetic resonance in the 1950s and 1960s were studying tiny samples, a few milliliters of purified liquid, sealed inside a narrow glass tube, sitting inside a small, precisely controlled magnet designed to fit on a benchtop. A human torso is not a tiny purified sample. It's an enormous, irregular, wet, breathing, moving three-dimensional structure, full of dozens of different tissue types layered against each other in complicated ways. Getting from one to the other wasn't a small technical step. It required, first, someone willing to believe the leap was even possible, and second, an entirely new conceptual trick that nobody in the chemistry world had any reason to invent, because chemists didn't need it. They already knew, more or less, what was in their tube. What they needed was structural detail at the molecular level, not a spatial picture of where things were located inside a larger object. The person who took the first real emotional and scientific leap toward imaging was a physician and physicist named Raymond Damadian, working at the State University of New York in the early 1970s. And Damadian's part in this story is worth telling slowly, because it's got both a genuinely important scientific insight buried inside it, and a very real, very human story of obsession, ambition, an eventual public grievance that the field has never fully settled, even now. Damadian's core hypothesis, which he began developing around 1971, was this. Cancerous tissue, he proposed, should have measurably different relaxation properties than healthy tissue. Now, we haven't fully explained relaxation properties yet. We'll come back and build that idea more carefully a little later, but for now, think of it loosely as a kind of signature, a way that different types of tissue respond differently once they've been nudged by a radio pulse, and then left to settle back down. Water in a tumor, Damadian reasoned, might behave differently, chemically and structurally, from water in ordinary healthy tissue. And if that difference was real and measurable, then in principle, you could use nuclear magnetic resonance not just to study chemistry, but to detect disease. Non-invasively, without cutting anyone open, without exposing anyone to ionizing radiation, just by measuring how the water inside a person's body responded to a magnetic pulse. Sit with that idea for a second, because it really is the emotional heart of this whole act of the story. A way to look for tumors inside a living person without hurting them at all. Damadian ran early experiments on excised rat tissue, comparing cancerous samples to healthy ones, and published his initial findings in the journal Science in 1971, reporting exactly the kind of difference his hypothesis predicted. It was a genuinely exciting result, and it planted a seed that would grow, over the following years, into something close to an obsession. Because having the hypothesis was one thing. Proving it could actually work on an entire living human being was another thing entirely, and Damadian threw himself into that second problem with a kind of stubborn, almost single-minded determination that his colleagues would later describe, depending on who you ask, as either visionary or exhausting, sometimes both at once. He founded his own company. He assembled a small team of collaborators, engineers and technicians willing to follow him into a project that most of the mainstream research world regarded, at the time, as far-fetched at best. And together, over years of painstaking, improvised, hand-built engineering, they constructed a full-body scanner large enough to actually fit a human being inside it. They gave it a name that tells you almost everything you need to know about Damadian's mindset during this period. He called it Indomitable. It was not a polished piece of commercial equipment. It was closer to something you'd expect to find in a garage workshop scaled up to room size, built from whatever components could be sourced and adapted, wired and rewired by hand, tested and retested against every obstacle that comes with trying to do something nobody has ever successfully done before. Colleagues who worked alongside Damadian during this period describe a laboratory culture built entirely around his singular focus, long nights, funding scraped together from wherever it could be found, a near-total unwillingness to accept that any particular obstacle might be permanent. He was, by most accounts, a difficult person to work for during these years, demanding, occasionally combative with skeptics, utterly convinced that what he was chasing was both real and urgently important, and largely uninterested in slowing down long enough to accommodate anyone who doubted him. That kind of obsessive, unyielding temperament doesn't always make for comfortable working conditions, but it's also, very often, exactly what it takes to drag a genuinely novel piece of engineering out of pure theory and into a physical, working object that has never existed before. Indomitable did not get built because the engineering was easy. It got built because one person refused to accept that it couldn't be done. And in July of 1977, after years of that grinding, obsessive work, Damadian and his team finally attempted the thing they had been building toward the entire time. A full-body scan of a living human volunteer, using Indomitable. It was not fast. It was not comfortable. It took nearly 5 hours, the subject holding as still as humanly possible for that entire span, while the machine, slowly, painstakingly, gathered enough signal to construct a single usable image. 5 hours is an almost unimaginable amount of time by the standards of modern medical imaging, where a scan today might take 20 minutes, sometimes less. But it worked. At the end of those 5 hours, there was an image. A picture, however crude by later standards, of the inside of a living human chest, produced not by cutting, not by radiation, but by listening to the whispered response of hydrogen atoms wobbling in a magnetic field. It's the kind of moment that deserves to be spoken of with the same reverence this field of storytelling usually reserves for the first controlled nuclear chain reaction, or the Wright brothers' first sustained flight. A moment where something that had only existed as an idea, an obsession, a hypothesis, suddenly, undeniably, worked. But Damadian's contribution, as important as it was, turned out not to be the piece that actually made imaging practical. And this is where the story turns toward another figure entirely, and toward one of those small, human, almost accidental moments that keep showing up throughout the history of physics, the kind of moment where a genuinely new idea arrives not in a laboratory, but somewhere far more mundane. Paul Lauterbur was a chemist, working at the State University of New York at Stony Brook in the early 1970s, and in 1973, he had an insight that deserves the same slow, careful unpacking that other great thought experiments in physics get, because on the surface it sounds like a small technical trick, and underneath, it's actually the conceptual key that unlocked the entire field of imaging. Here's the problem Lauterbur was staring at. Nuclear magnetic resonance, as it existed at that point, could tell you an enormous amount about the chemistry happening inside a sample. It could tell you what kinds of atoms were present, roughly how much of each, even subtle details about their chemical environment. What it could not tell you, not without some new trick, was where inside the sample any of that signal was coming from. If you put a whole human torso into a uniform magnetic field, and every single hydrogen atom in that torso was sitting in exactly the same field strength, then every single one of them would be wobbling at exactly the same frequency. The signal coming back would just be one giant blur, a single averaged hum representing every hydrogen atom in the body all mixed together, with absolutely no way to tell which part of that hum came from the chest, and which came from the abdomen, and which came from anywhere else. You'd have chemistry without geography. And geography, spatial location, is the entire point of medical imaging. Lauterbur's insight was to deliberately break the uniformity of the magnetic field on purpose in a very precise, controlled way. Instead of one single field strength across the entire sample, what if you overlaid a second, much weaker magnetic field on top of the main one, a field that varied smoothly and predictably from one end of the sample to the other, stronger at one end, weaker at the other? Remember from earlier, the precession frequency of a proton depends exactly on the strength of the magnetic field it's sitting in. So if the field strength itself is now different at different points inside the sample, then the precession frequency, the wobble rate, will also be different at different points inside the sample. A hydrogen atom sitting at the strong end of that gradient will wobble faster. A hydrogen atom sitting at the weak end will wobble slower. And suddenly, frequency itself becomes a map of position. Picture it concretely for a moment, the way you might picture a very long, very orderly choir stretched out in a line, each singer positioned at a different point along that line. Ordinarily, if you asked the whole choir to hum the exact same note, you'd get one uniform, blended sound with no way to tell where inside the line any individual singer was standing. But now imagine you very gently and precisely retuned the room itself, so that acoustics near one end of the line naturally make voices sound very slightly lower, and acoustics near the other end make voices sound very slightly higher, smoothly and predictably shifting in between. Now, when the whole choir hums together, you get a smeared, continuous range of pitches rather than one single note, and crucially, that range of pitches directly corresponds to physical position along the line. A listener who can precisely measure pitch can now work out exactly where along the line any particular voice was standing, just from the sound alone. That's the trick Lauterbur had found a way to apply to hydrogen atoms scattered through a human body, using a deliberately imposed gradient in magnetic field strength instead of an imagined shift in room acoustics. This deserves the same slow unpacking that a great thought experiment about trains and lightning gets in other physics stories, because it really is that elegant a leap. By deliberately imposing an imperfect, gradient magnetic field, Lauterbur had found a way to encode spatial position directly into the one thing his equipment could actually measure: frequency. Listen to the signal coming back from the sample. Break it down into its individual component frequencies, and you're no longer just listening to an averaged hum. You're listening to a whole chorus of individual voices, each one singing at a slightly different pitch depending on exactly where inside the sample it's located. Decode those frequencies correctly, and you've got a map. You've got an image. There's a story about how this idea first arrived to Lauterbur, and it deserves to be told in full, because it's the kind of small, human, almost embarrassingly ordinary detail that makes these histories feel real rather than mythical. The story goes that the core insight came to him not at a chalkboard, not in a laboratory, but at a fast food restaurant, where he sketched the basic concept out on a napkin while sitting there, working through the geometry of gradient fields and resonance frequencies in his head, translating a half-formed idea into something concrete enough to write down before it slipped away. Whatever the precise details, the essential picture holds. One of the most consequential ideas in the history of medical technology, an idea that would eventually let doctors see inside living human bodies without cutting them open, first took shape as a few scribbled lines on a paper napkin, in a completely unremarkable, human-scale moment, the kind of moment that happens to all of us, except that for Lauterbur, it happened to be the moment his mind finally clicked the last piece of a puzzle into place. Lauterbur published his idea in 1973 in the journal Nature, describing what he called zygmatography, a name that never really caught on, mercifully, and which was eventually replaced by the far more sensible term magnetic resonance imaging. But even with Lauterbur's gradient field trick in hand, there was still a serious practical gap between the theory and anything you could actually use in a hospital. The mathematics required to reconstruct a genuinely useful image, and the speed at which that image could be gathered, still had a long way to go before this technique could move from proof of concept to something that could scan an actual patient in a clinically reasonable amount of time. That's where Peter Mansfield comes into the story, a physicist working at the University of Nottingham in England, whose contribution was less about the initial conceptual leap and more about the hard, unglamorous, absolutely essential work of turning a research curiosity into something clinically usable. Mansfield developed the mathematical framework and the pulse sequence techniques, most famously something called echoplanar imaging, that allowed the raw signal to be captured and processed dramatically faster than earlier methods allowed. Where Damadian's Indomitable had needed nearly 5 hours to produce a single crude image, Mansfield's techniques, refined and built upon over the following years, eventually opened the door to scans that could be completed in minutes rather than hours, turning magnetic resonance imaging from an extraordinary laboratory demonstration into something that could genuinely function inside a hospital, on a schedule, with real patients waiting their turn. So by the mid to late 1970s, you have 3 men, working largely independently, each contributing an essential piece. Damadian, driven by a hypothesis about detecting cancer, providing the obsessive, almost evangelical drive to prove that full-body human scanning was even possible at all, and physically building the first machine that did it. Lauterbur, providing the conceptual key, the gradient field trick that turned an averaged chemical hum into a genuine spatial map. And Mansfield, providing the mathematical and engineering refinement that made the whole process fast enough to be clinically practical. 3 very different contributions, 3 very different temperaments, converging on the same technology from 3 different directions. And this is where the story takes a turn that needs to be told carefully, even-handedly, without trying to adjudicate who was really right or really wrong, because reasonable, well-informed people have disagreed about it for decades, and probably always will. In 2003, the Nobel Prize in Physiology or Medicine was awarded for the development of magnetic resonance imaging. The recipients were Paul Lauterbur and Peter Mansfield. Raymond Damadian was not included, and Damadian did not take this quietly. He believed, passionately and publicly, that his own contribution, the founding hypothesis about tissue relaxation differences, the years of obsessive engineering work, the construction of Indomitable, the actual first full-body scan of a living human being, deserved recognition equal to what Lauterbur and Mansfield received. He took out full-page advertisements in major newspapers, arguing his case directly to the public, since the Nobel Committee's decision was, and remains, final and unappealable. The scientific community itself was divided on the matter, and remains divided even now. Some prominent physicists and radiologists publicly supported Damadian's case in the aftermath of the announcement, arguing that without his founding hypothesis and his willingness to build the first working full-body scanner, the entire clinical application of the technology might have taken years longer to arrive, or might have emerged in a different, less complete form entirely. Others pointed out that scientific priority disputes of this kind are almost never as clean as either side wants them to be, that ideas rarely belong entirely to one person, that Lauterbur's gradient trick and Mansfield's fast imaging mathematics were, in their own right, independently necessary breakthroughs, without which Damadian's founding hypothesis would have remained clinically impractical regardless of how correct it eventually turned out to be. It's worth handling this the same even-handed way this kind of story gets handled elsewhere in the history of science. The way people talk about the fallout between the inventors of the transistor, or the long-running priority dispute between Einstein and Hilbert over the equations of general relativity. There isn't a clean, satisfying answer here about who was really robbed. What can be said, fairly, is this. Nobel Prizes are limited to 3 recipients per category per year, a rule that has created uncomfortable omissions many times throughout the prize's history, and the committee's specific citation credited Lauterbur and Mansfield for the 2 technical breakthroughs, spatial encoding through gradient fields and fast image acquisition, that made imaging practical as a general technique. Damadian's hypothesis about tissue relaxation differences, meanwhile, though scientifically important and historically foundational to the whole effort, turned out not to be quite as clean or as universally reliable a diagnostic tool as he'd originally hoped, even though, as we'll see later, the underlying physical difference he identified turned out to be real, and turned out to become one of the central pillars of how modern scanners actually generate their images. Whatever the committee's precise reasoning, Damadian's public protest reflected a genuine, deeply felt wound. The pain of watching a technology you helped bring into the world receive its highest honor without your name attached to it. That's a real human thing to sit with, and the story doesn't need to resolve it neatly to be worth telling honestly. What matters, for where we're headed next, is that by the late 1970s, all the essential pieces were now sitting on the table. A way to generate a resonance signal from bulk tissue. A way to encode spatial position into that signal using gradient fields. A way to gather that signal fast enough to be clinically useful. The idea had made its leap from chemistry bench to hospital hallway. What remained, and what would occupy the next chapter of this story, was the extraordinarily difficult engineering task of actually building a machine that could do all of this reliably, safely, and repeatedly for real patients in real hospitals around the world. Let's shift gears now from history into engineering, the same kind of turn you'd expect once an idea moves from theory into something people actually have to build, wire, cool, and keep running day after day inside a working hospital. Because everything we've talked about so far, the wobbling protons, the gradient fields, the resonance, all of it depends on one enormous, expensive, physically demanding piece of hardware sitting at the center of the whole machine. The magnet. Here's why the magnet has to be so extreme. Remember that tiny statistical surplus of aligned protons we talked about earlier, that whisper-thin excess left over after nearly all the protons cancel each other out. That surplus, faint as it already is, only exists because of the strength of the external magnetic field pulling on it. A weak magnetic field produces an even weaker surplus, an even fainter signal, and at some point, if the field isn't strong enough, there simply isn't enough signal left to detect at all, buried hopelessly under noise. So the whole enterprise depends on building the strongest, most uniform magnetic field that can practically be constructed around a space large enough to fit an entire human body. To get a sense of scale here, magnetic field strength is measured in a unit called the Tesla, and a typical clinical scanner operates somewhere between 1.5 and 3 Tesla, with research scanners sometimes pushing considerably higher. The Earth's own magnetic field, the one that makes a compass needle point north, is roughly 50 microtesla, a tiny fraction of a single Tesla. So even a modest clinical scanner is generating a magnetic field many thousands of times stronger than the entire planet's own magnetism, concentrated into a space just large enough to hold a person. Generating a field that's strong, using an ordinary electromagnet, an ordinary coil of wire with electricity flowing through it, runs into an immediate and brutal problem. Ordinary wire has electrical resistance, and resistance means that as current flows through it, energy gets lost as heat, and the more current you push through to generate a stronger field, the more heat you generate, until you're looking at a wildly impractical amount of power consumption and cooling just to keep the coil from melting itself. This is where the story takes one of its most genuinely strange turns, into a piece of physics that sounds almost like a magic trick the first time you hear it explained. There's a class of materials that, when cooled down to extremely low temperatures, undergo a change so dramatic it seems to violate ordinary intuition about how electrical circuits are supposed to behave. Their electrical resistance doesn't just decrease as you cool them. It vanishes entirely, completely. Not approximately zero, but genuinely, measurably, as close to absolute zero resistance as physics allows. This phenomenon is called superconductivity, and it was first observed back in 1911 by a Dutch physicist named Heike Kamerlingh-Onnes, working with mercury cooled to just a few degrees above absolute zero, and it remained, for decades, a fascinating but largely academic curiosity, a strange low-temperature quirk of certain materials that didn't have an obvious practical application, until the age of medical imaging came along and needed exactly this property to make its enormous magnets even remotely feasible. Here's why superconductivity matters so much for an MRI scanner. If you build the main magnet's coil out of a superconducting material and cool it down below its critical temperature, then once you start current flowing through that coil, it keeps flowing indefinitely, without any additional power input, without any resistance to fight against, without generating heat that needs to be continuously removed. You start the current flowing once, close the loop, and it just keeps circulating, generating a stable, powerful magnetic field for years, potentially for decades, essentially for as long as you keep the coil cold enough to stay superconducting. And that's exactly why, if you've ever wondered, the magnet inside an MRI scanner is never actually switched off between patients, not overnight, not on weekends, not even when the hospital is closed. Turning a superconducting magnet on and off isn't like flipping a light switch. The current, once established, is meant to keep circulating continuously, and the enormous magnetic field it generates is simply always there, always on, silently filling the scanner room around the clock, whether or not anyone happens to be lying inside it at that particular moment. There's another requirement sitting alongside raw field strength that deserves its own moment of attention, because strength alone isn't enough. The field also has to be extraordinarily uniform across the entire space a human body occupies inside the scanner. Remember that the precise frequency at which a proton wobbles depends exactly on the local field strength it experiences. If the field varied unpredictably from one point to another inside the scanner in some uncontrolled, accidental way, separate from the carefully engineered gradient fields we'll get to shortly, then the resulting frequencies coming back from the body would be scrambled by noise the machine never intended to introduce, and the resulting images would be smeared, distorted, unreliable. Engineers spend an enormous amount of effort on a process called shimming, fine-tuning the magnet, sometimes with small additional correction coils, sometimes with careful physical adjustments, to iron out any tiny irregularities in the field until it's uniform to a truly remarkable degree across the entire imaging volume. It's the kind of unglamorous, painstaking precision work that never shows up in a headline, but without it, none of the rest of the machine's cleverness would produce anything usable. To keep the coil cold enough for superconductivity, most clinical scanners use liquid helium, cooled down to somewhere around 4 degrees above absolute zero, an almost inconceivably cold temperature, colder than the vacuum of deep space in most parts of the universe. The coil sits submerged inside a sealed, heavily insulated container called a cryostat, essentially an enormous, extraordinarily sophisticated thermos bottle, designed to keep that liquid helium from boiling away and warming the coil back up to the point where superconductivity breaks down. And this brings us to one of those genuinely vivid, slightly frightening engineering stories that this kind of deep dive tends to circle back to, the kind of controlled danger detour that sits alongside stories like the Boston molasses tank collapse or the diesel generator failures at Fukushima, a moment where an ordinary, carefully managed system reveals just how much raw physical force it's actually holding in check. If, for any reason, a section of that superconducting coil loses its superconductivity, even briefly, even locally, something called a quench occurs. The moment even a small part of the coil regains electrical resistance, all that circulating current, which had been flowing frictionlessly for years, suddenly encounters resistance again, and that resistance generates heat, rapidly, catastrophically, in a runaway feedback loop that spreads through the entire coil within seconds. All the energy that had been quietly stored in that magnetic field gets dumped, essentially all at once, as heat, and that heat instantly boils off the liquid helium surrounding the coil, converting it from a cold liquid into an enormous volume of extremely cold gas almost instantaneously. Liquid helium expands by a factor of many hundreds when it turns to gas, and a quench can release that gas violently enough that scanner rooms are built with dedicated venting systems, pipes designed to carry that suddenly expanding helium gas safely up and out of the building entirely, specifically so that it doesn't displace all the breathable air in the room and put anyone inside at risk of suffocation. It's rare. Modern scanners are engineered carefully to avoid it happening accidentally. But it's a real, planned-for event, and every scanner room's ventilation system exists, in part, because of it. There have been documented cases over the years where venting systems failed or were undersized for the volume of gas actually released, and rooms filled with enough displaced, oxygen-poor helium gas that people inside needed to be evacuated quickly, a stark reminder that even a slow, quiet, permanently humming machine is, underneath all that quiet, storing an enormous amount of physical energy that has to go somewhere the instant the underlying physics stops cooperating. It's worth pausing here to notice something almost philosophically strange about the whole arrangement. A quench happens because superconductivity, this seemingly magical, frictionless flow of electrical current, is itself a fragile state, entirely dependent on temperature staying below a very specific threshold. Warm the coil up by even a small amount, whether through some mechanical disturbance, some tiny imperfection in the cooling system, or in rare cases a deliberate emergency shutdown triggered by hospital staff to protect someone in danger inside the room, and the whole elegant frictionless system collapses back into ordinary resistive wire almost instantly, releasing years' worth of quietly stored magnetic energy in a matter of seconds. The same property that makes the machine possible at all is also the property that makes it, in a very real sense, always sitting right at the edge of a dramatic, sudden, physically forceful event, carefully and continuously managed to make sure that edge is never actually reached by accident. That's also why the culture around metal safety in a scanner room is treated with such unwavering seriousness, and why hospitals train every single staff member, not just radiology technicians, but nurses, janitorial staff, visiting physicians, anyone who might ever set foot near the room, to understand exactly what's at stake. There are documented, real incidents, some of them tragic, where an overlooked metal object, an oxygen cylinder brought in during an emergency, without anyone checking it first, a metal chair, even a mislaid pair of keys, has been pulled violently across the room the instant it entered the field, accelerating with startling speed toward the bore of the magnet. In more than one case, patients or staff standing between the object and the magnet have been seriously injured or killed. These incidents are rare precisely because the safety culture around them is taken so seriously: layered screening, metal detectors, standardized checklists before anyone enters the room. But they're rare because of that vigilance, not because the underlying danger isn't real. It's one of the clearest, starkest examples in all of modern medicine of an invisible, silent, permanently active field translating directly into concrete physical consequence the moment ordinary caution slips. That enormous, permanently active magnetic field is also the reason behind one of the most rigorously enforced safety cultures in all of hospital medicine: the strict, absolute rule that nothing metal, nothing ferromagnetic, ever enters the scanner room uncontrolled. This isn't an abstract precaution. There have been real, documented, deeply sobering incidents where ordinary metal objects, an oxygen tank left carelessly nearby, a wheelchair rolled too close, even something as small as a pair of scissors or a hairpin, have been violently yanked across the room by the magnet's pull, becoming, in effect, dangerous projectiles, traveling fast enough and with enough force to cause serious, sometimes fatal, injury to anyone standing between the object and the magnet's core. Hospitals train their staff on this constantly, screen every single person entering the room with real rigor, precisely because an invisible, permanently active field that's strong doesn't forgive a moment's carelessness. It's one of the clearest examples in modern medicine of an abstract piece of physics, the magnetic force between materials, translating directly into concrete, physical, human stakes. So that's the magnet. An enormous, permanently active, superconducting ring, cooled to near absolute zero, generating a field thousands of times stronger than the Earth's own, silently maintaining that field around the clock, year after year, so that the tiny statistical surplus of aligned protons in a patient's body has something strong enough to align against in the first place. But the magnet alone only gets you the uniform alignment. Turning that alignment into an actual, spatially resolved image of the inside of a human body requires a whole additional layer of engineering. And that's where we're headed next. Let's build the rest of the machine now, layer by layer, starting with the part that grew directly out of Lauterber's napkin sketch all those years earlier. The gradient coils. If the main superconducting magnet provides the enormous, uniform background field, the gradient coils are what deliberately, precisely disrupt that uniformity in a controlled way. Exactly the trick Lauterber first worked out, but now built into real hardware, arranged in 3 separate sets, one for each spatial direction, so the machine can vary the field strength smoothly along the length of the body, across its width, and through its depth, all independently, all under precise electronic control. This is worth slowing down for, because it's really the conceptual heart of the entire machine, the direct mechanical descendant of that idea sketched out on a napkin decades ago. By rapidly and precisely varying these gradient fields during the scanning process, the machine can control, moment by moment, exactly which slice of the body, which narrow cross-section, is currently in resonance with a given radio frequency pulse. Turn on a gradient along one axis, and only the protons sitting within a very specific, narrow band of field strength, and therefore a very specific, narrow physical slice of the patient's body, will be wobbling at the exact frequency the machine is about to send in. Everything outside that slice is wobbling at a different frequency and simply won't respond. This is how the machine builds up its image, slice by slice, layer by layer, methodically working through the entire volume of the body being scanned, all controlled by these 3 sets of gradient coils working together in careful, rapidly shifting combination. Working alongside the gradient coils are the radio frequency coils, which handle the actual sending and receiving of signal. There's a lovely symmetry here that connects back to something from the very opening of tonight's story, the idea of listening. The RF coils send in a precisely tuned pulse of radio energy, timed exactly to match the resonance frequency of the protons in whatever slice is currently selected by the gradient fields, and that pulse briefly tips those aligned protons out of their resting alignment. Then, and this is the part worth appreciating, the coils fall completely silent. They stop transmitting and switch into listening mode, waiting to detect the extremely faint radio signal that comes back as those disturbed protons relax back down into their original alignment with the main magnetic field. It's an active, alternating rhythm, speak, then listen, speak, then listen, thousands of times over the course of a scan, each cycle gathering a little more of the raw data that will eventually be assembled into an image. And that relaxation process, the way the protons settle back down after being disturbed, brings us back to Damadian's original hypothesis from years earlier, the one about cancerous tissue behaving differently from healthy tissue, and it's worth reintroducing it here, more fully, because this is where it turns out to have been genuinely, importantly right. Even if the full picture ended up being more complicated and more useful than his earliest experiments suggested. Let's slow down here, because this deserves the same patient unpacking the earlier parts of tonight's story have gotten, and it really is the conceptual heart of how a finished scan ends up looking the way it does. When that RF pulse tips the aligned protons out of their resting position, 2 separate things start happening to them at once, on 2 separate timescales, and both of those separate processes carry useful diagnostic information. The first process, called T1 relaxation, describes how quickly the protons realign themselves back with the main external magnetic field, recovering their original orientation. This recovery happens because the disturbed protons are constantly exchanging energy with their surrounding molecular environment, sometimes called the lattice, bumping against neighboring molecules, losing the extra energy the RF pulse gave them back into their surroundings. How efficiently that energy exchange happens depends heavily on what kind of tissue the protons are actually sitting inside. Water molecules floating freely in something like cerebrospinal fluid tumble around quickly and somewhat inefficiently exchange energy with their surroundings, so they take a relatively long time to realign, a long T1. Fat molecules, by contrast, have a very different molecular structure, and their protons exchange energy with their surroundings far more efficiently, realigning much faster, a short T1. The second process, T2 relaxation, is subtly different, and it describes something happening among the protons themselves rather than between the protons and their broader surroundings. Immediately after the RF pulse, all the disturbed protons are, briefly, precessing in step with each other, synchronized, all wobbling together in phase. But tiny local variations in the magnetic environment, differences from one molecule to the next, cause them to gradually drift out of step with each other, dephasing. And as they dephase, the collective signal they generate together weakens and fades, even before they've fully realigned with the main field. How quickly that dephasing happens, again, depends on the specific tissue, on how tightly packed and structurally organized the local molecular environment is. Put those two clocks together, T1 telling you how quickly protons realign with the main field, T2 telling you how quickly they fall out of step with each other, and you get a rich, tissue-specific fingerprint. Different pulse sequences can be designed to emphasize one clock over the other, producing images where fat appears bright and fluid appears dark, or the reverse, depending entirely on which relaxation process the radiologist wants highlighted for a particular diagnostic question. There are actually these two separate relaxation processes happening simultaneously, conventionally labeled T1 and T2, and different tissue types relax through these two processes at different, measurable rates. Fat tissue relaxes differently from water. Healthy tissue relaxes differently from many kinds of diseased or abnormal tissue. Cerebrospinal fluid relaxes differently from white matter in the brain, which relaxes differently again from gray matter. These differences in relaxation rate are not a side detail. They are, in a very real sense, the actual diagnostic content that a radiologist is reading when they look at a finished scan. The contrast you see in an MRI image, the reason a tumor can sometimes be distinguished from surrounding healthy tissue, the reason different structures inside the brain appear as different shades and textures, all of it comes down to these tissue-specific differences in relaxation behavior, first hypothesized, in that early, obsessive, not yet fully proven form, by Raymond Damadian back in 1971. His founding intuition turned out to be exactly right. It just took the rest of the machine, the gradient coils, the imaging mathematics, decades of refinement, to turn that intuition into something you could actually see. But here's the genuinely hard part, the piece that requires stepping back and thinking mathematically for a moment. The raw signal the RF coils actually pick up isn't a neat, ready-made picture. It's an enormous, scrambled jumble of overlapping frequencies, all of them arriving at the detector simultaneously, encoding both spatial position and tissue relaxation information all tangled together in one messy stream of data. This raw data lives in something mathematicians and physicists call K-space, a kind of frequency map that has to be mathematically unscrambled before it turns into anything resembling a recognizable image. The tool that does the unscrambling is called the Fourier transform, and rather than getting lost in equations, think about it this way. Imagine listening to a full orchestra playing a chord, dozens of instruments all sounding at once, blended together into a single, complex wave of sound reaching your ears. Your ear, remarkably, can sometimes pick out individual instruments within that blended sound, but doing it with mathematical precision, taking that single complicated wave and cleanly separating out exactly which frequencies came from the violins, which from the cellos, which from the brass, requires a systematic mathematical process. The Fourier transform does exactly this kind of unmixing, but for the raw radio signal coming back from a patient's body. It takes that single, tangled stream of overlapping frequencies and systematically separates it back out into its individual components, each one corresponding to a specific spatial location within the body, thanks to the gradient encoding trick we just walked through. Do this unmixing correctly across the entire volume of collected data, and what emerges, almost like magic, though it's really just careful mathematics, is a genuine spatial image. A picture. There's a further layer of subtlety worth adding to the case-based picture, because it explains something that seems paradoxical at first. The raw data isn't collected all at once, the way a camera might capture an entire image in a single instant. It's built up gradually, one narrow strip of frequency data at a time, gathered across many repeated cycles of that speak-then-listen rhythm, each cycle contributing one more line to the overall case-based map, before the Fourier transform can finally be applied to the completed collection and turn it into a picture. This is part of why patient movement during a scan is such a persistent, practical problem. Because the raw data is assembled gradually, across potentially hundreds of repeated cycles, any movement partway through the process corrupts the relationship between different pieces of the collected data, and the resulting image comes out blurred, doubled, smeared in exactly the way a long-exposure photograph blurs if the subject shifts partway through the shot. It's also why technologists spend real effort padding, bracing, and instructing patients before a scan even begins, because the underlying mathematics genuinely does depend on staying still for the whole duration. This whole process explains why scans take the time they take, and why there's an inescapable trade-off between resolution, how finely detailed the final image is, signal to noise, how clean and clear the image looks, and scan duration, how long the patient has to lie still inside the machine. Gathering more data, more slices, finer detail, cleaner signal, simply takes more time, more repetitions of that speak-then-listen cycle, and radiologists and technicians are constantly balancing these competing demands against each other, against the practical limits of how long a patient can reasonably be expected to hold still, against the clinical urgency of the particular question the scan is trying to answer. And now, finally, we arrive at the sound. That infamous, unmistakable, jarringly loud banging and clanking that anyone who has ever been inside one of these machines remembers vividly. The sound that seems so wildly out of place inside a quiet hospital, so at odds with the whole point of the procedure. Here's where that sound actually comes from, and it's a genuinely strong sensory beat worth sitting with for a moment before we move on. Remember the gradient coils, rapidly switching their magnetic fields on and off, thousands of times over the course of a scan, to select different slices of the body. Those coils are carrying substantial electrical current, and they're sitting inside the enormous, permanently active magnetic field of the main superconducting magnet. Whenever a current-carrying wire sits inside a magnetic field, it experiences a physical force called the Lorentz force, a force that pushes and pulls on the wire itself. And because the gradient coils are switching on and off so rapidly, thousands of times per second in some sequences, they're being physically pushed and pulled, flexed, ever so slightly, thousands of times per second, and that rapid mechanical flexing is what generates the sound. It's not electronic. It's not a speaker playing a recording. It's the actual physical structure of the machine vibrating under real mechanical force, sometimes reaching well over 100 decibels, loud enough that patients are always given hearing protection before a scan begins. There's a real paradox worth sitting with here, and it's one of the more strangely poetic details in the whole story. An enormously loud machine, built for the singular purpose of keeping a person as still and calm as possible, generating a jarring, mechanical racket precisely because of the same underlying physics that lets it see so gently and so precisely into the human body. The gentleness and the noise come from the exact same source. You can't have one without the other. Let's move now from the physics laboratory into the hospital hallway, into the wider world where this machine actually found its place. Through the 1980s, magnetic resonance imaging spread rapidly from a handful of pioneering research institutions into commercial availability, the first commercial scanners becoming operational in hospitals across the United States, Europe, and Japan over the course of that decade. It wasn't cheap. It still isn't. The enormous superconducting magnets, the cryogenic cooling systems, the precision electronics, all of it adds up to equipment costing millions of dollars, and questions about cost and access have followed the technology ever since. Questions about which hospitals can afford to install a scanner, which patients have insurance coverage that makes a scan affordable, which parts of the world have ready access to this kind of imaging and which don't. The rollout wasn't instantaneous or evenly distributed, either, and it's worth acknowledging that honestly rather than smoothing it into a simple story of triumphant progress. Early commercial scanners were temperamental, expensive to maintain, and required specially trained staff who, in the early years, sometimes had to be trained essentially from scratch, since almost nobody outside a handful of research institutions had any practical experience running one of these machines. Large academic hospitals in wealthy countries got first access, unsurprisingly, and it would take considerably longer for the technology to reach smaller hospitals, rural areas, and much of the developing world, a pattern of uneven access that, in some places, persists to this day. None of that undercuts how remarkable the underlying achievement was. It's just worth remembering that a scientific breakthrough and a fully realized, universally accessible medical tool are two different things, separated by years, sometimes decades, of unglamorous infrastructure work, training programs, cost negotiations, and slow, patient institutional change. One of the most remarkable extensions of the core technology came with the development of functional MRI, usually just called fMRI, which takes the same basic hardware and points it at a slightly different question. Rather than imaging the static anatomical structure of tissue, functional MRI detects small changes in blood oxygenation that occur in different regions of the brain, depending on how actively those regions are being used at any given moment. Active neurons demand more oxygen, and that demand produces a detectable, if subtle, change in the local magnetic signal. The remarkable result is a technique that lets researchers watch, in something close to real time, which regions of a living human brain light up with activity while a person performs a task, solves a problem, recognizes a face, recalls a memory. It's the kind of abstract physics becoming something almost magical turn that shows up again and again in this niche's favorite stories. The same basic transformation you see when quantum entanglement becomes quantum computing or when stimulated emission becomes the laser. Here, the quiet physics of hydrogen nuclei wobbling in a magnetic field becomes, almost improbably, a window into the working of thought itself. Contrast agents deserve a brief mention here too. Certain compounds, most commonly ones containing the element gadolinium, can be safely injected into a patient's bloodstream before a scan, and they work by altering the local magnetic environment around the tissue they pass through, making certain structures, blood vessels, areas of inflammation, certain tumors, show up with much sharper contrast against their surroundings. Gadolinium itself is a rare earth metal with unusual magnetic properties, 7 unpaired electrons sitting in its outer shell, giving it an especially strong magnetic personality of its own, strong enough that even in the tiny, carefully controlled doses used in a contrast injection, it noticeably speeds up the relaxation of nearby hydrogen nuclei, brightening the signal from whatever tissue it happens to be circulating through at the time. It's a relatively simple addition to the underlying physics, but a clinically important one, giving radiologists another tool for distinguishing exactly what they're looking at, particularly useful for spotting subtle areas of inflammation or abnormal blood vessel growth that might otherwise blend too closely into their surroundings to be reliably identified. There's also a quieter, more humane history worth mentioning around how the experience of being scanned has slowly, gradually improved over the decades. Early scanners offered patients essentially nothing in the way of comfort, a narrow tube, a loud noise, and an instruction to hold still for however long the sequence required. Over time, manufacturers began experimenting with wider bore designs, giving patients a little more physical breathing room inside the tube. Open MRI variants, mentioned briefly a moment ago, went further still, sacrificing some magnetic field strength and therefore some image sharpness in exchange for a design that leaves the sides of the machine open, dramatically easing the experience for patients who find enclosed spaces genuinely distressing. Mirror systems and prism glasses were developed that let a patient lying flat inside the tube see out toward the room or watch a film, rather than staring up at featureless plastic inches from their face. None of these innovations change the underlying physics in any fundamental way. They simply reflect decades of accumulated, practical attention to the fact that the person inside the machine is not an abstraction, but an anxious, breathing human being who has to actually tolerate the experience for it to do any good at all. And it's worth pausing, before this act closes, on some of the more humane, grounding details that came along as the technology matured. Open MRI variants were developed for patients who struggle with the claustrophobia of a traditional closed-tube scanner, trading a small amount of image quality for a design that leaves the sides more open, less enclosing. Pediatric sedation protocols were developed carefully over years of clinical practice to help young children who simply cannot be expected to lie still and calm for the duration of a scan on their own. None of this made headlines the way the original discoveries did, but all of it reflects the slow, careful, ongoing work of turning an extraordinary piece of physics into something that could actually, gently, be used on real, anxious, sometimes frightened human beings. As for where the technology stands now, there are ongoing frontiers worth a light mention before we turn toward the close of tonight's story. Researchers continue pushing toward higher field strength magnets, offering ever finer image detail. Faster pulse sequences continue to shrink scan times, easing the burden on patients who once had to hold still for hours the way Damadian's earliest volunteer did. And increasingly, artificial intelligence techniques are being applied to the image reconstruction process itself, helping extract clearer pictures from less raw data, potentially shortening scan times even further. These are real, active areas of research, but this particular kind of story tends to gesture lightly at the present and future rather than dwell there, and so we will too, and turn instead toward something quieter. Because it's worth zooming back out now, all the way out, away from the engineering, away from the history, away from the Tesla and the gradient coils and the Fourier transforms, back to where we started. Back to you, lying there, and the strange, invisible thing happening inside your own body right now, and will keep happening long after you fall asleep. Every hydrogen atom in you is still spinning, still precessing, quietly, indifferent to whether anyone is paying attention to it or not, indifferent to whether it's the middle of the night or the middle of a busy afternoon, indifferent to being observed or ignored entirely. It doesn't know that a Swiss-born physicist and an American radar researcher spent years working out how to detect it. It doesn't know that a chemist once sketched an idea about it on a napkin in a fast food restaurant. It doesn't know that a driven, obsessive researcher built a 5-hour machine and called it indomitable, or that decades later, people would argue in newspaper advertisements about who deserved credit for what. It just spins. It's been spinning since long before any of that history happened, and it will keep spinning after you've forgotten every detail of tonight's story, which is completely fine. That's what it's there for. Think for a moment about everyone this story has passed through. A quiet, methodical man from the Lower East Side, patiently sorting molecular beams in a basement laboratory, never imagining his resonance technique would one day let doctors look inside a living chest. A Swiss physicist and a wartime radar engineer, working on opposite coasts, arriving at the same discovery within weeks of each other, without any bitterness between them when the credit came to be shared. A driven, obsessive researcher who built a 5-hour machine by hand and called it indomitable, because that's exactly what the whole endeavor had demanded of him. A chemist who once sketched the key to spatial imaging on a paper napkin in a fast food restaurant, half-formed thoughts crystallizing into an idea that would eventually let mathematics unscramble the geography hidden inside a scrambled radio signal. An English physicist who took that raw idea and made it fast enough to actually use on a real, waiting patient. None of them set out, at the very beginning, to build a machine that would eventually sit quietly humming in tens of thousands of hospitals around the world. They were mostly just chasing a stubborn, specific question, one small piece of a much larger puzzle, not knowing exactly where it would lead, or whether it would lead anywhere useful at all. That's true of most of the deepest, most consequential ideas in the history of science. Nobody sets out to build the whole cathedral. They just keep laying one careful stone after another, and sometimes, decades later, if enough stubborn people keep at it long enough, a cathedral turns out to be standing there after all. And somewhere out there tonight, in a hospital not too far from wherever you happen to be lying right now, a superconducting magnet is quietly doing the same thing it's been doing for years without interruption. Always on, never switched off between patients. Sitting there in the dark of an empty scanner room, patiently maintained near absolute zero, its enormous invisible field filling the room around it, waiting for tomorrow's first patient, existing at all only because a century's worth of curious, stubborn people kept asking questions about something as strange and as quietly poetic as a spinning atom. So let that be the last thing you carry with you tonight. No rush at all. If you're already halfway gone, the ideas will still be here whenever you want them again. Somewhere, right now, a hospital is humming with an invisible magnetic field built to see inside people gently. And somewhere closer, right there in your own chest, your own hands, your own slowing breath, the same quiet, ancient, endlessly patient spin is still turning, the way it always has, the way it always will, whether you're awake to notice it or not. Let your breathing settle. Let the thoughts get looser, less organized, drifting the way they do right before sleep finally takes over. There's nothing left to do tonight, but let it happen.